Welcome back to everyone that has been in the morning session. And welcome to all of you that have joined just for the afternoon session. Today, this afternoon, we're going to discuss safety of automated driving, as I said. It's a joint workshop, as we have called it, between Euro NCAP, celebrating 20 years of Euro NCAP today, and the Okobi conference, which will start tomorrow at the Elsenveld here in Antwerp for the next 3 days. Okobi is, of course, a long-running conference on safety, on biomechanics, on automotive and non-automotive. But of course, the world is changing around us, and Okobi has to change with it. So in the last couple of years, more and more topics related to active safety and also automated driving have become part of the Okobi work. The workshop will be moderated by myself and Anders Lee, that you have heard this morning and saw in some of the clips. But before that, I want to give the word to Ola Bostrom from Autoliv to say a few words on behalf of Okobi.
So, on behalf of the Okobi Council, I welcome you all, especially all people that are attending the conference that is taking place in the rest of the week. I hope that after this workshop, you have learned a lot that you can be of benefit of to understand what is needed in biomechanic research the coming 20 years.
All right, so what we have prepared for you this afternoon is actually a couple of presentations, speeches by, I think, very renowned experts in this field. We've tried to have different aspects represented in this afternoon's program, from policy making and consumer and the work that NCAP is doing as part of the Roadmap 2025, to the development of sensors, vehicle interior, because the subject of automated driving is so wide and so big, we really have to make sure that we can cover at least some of the most important critical aspects when we talk about safety. So without further ado, I would suggest that we go down below, and Anders comes up and introduces the first speaker. Thank you.
Yes, good afternoon, everyone. It's a pleasure to be here live, not only on the scene. We have a very exciting afternoon in front of us. We have nice presentations, and I will do my speech in between as short as possible. Our first presenter is Professor André Sieck from the German Highway Research Institute, and he's going to talk about automated driving policies and consumer perspectives. He's a long-time friend and colleague and sometimes discussant from the Euro NCAP Board of Directors, and he has also been the president of Euro NCAP for a very important period. And now he's further, on top of that, also chairing the strategic working group on automated driving. So he's a very good person to talk about the automation, the challenges, policies, and consumer perspectives. Please, André.
Yes, Anders, thank you very much for this kind introduction. Ladies and gentlemen, I'm proud to be here and to be the first speaker for this workshop about automated driving. And yes, I have many slides and I try to compress it into 20 minutes. So I don't want to waste time. I am speaking here with two heads. First, with the head of BAST, of the German Research Institute for Highway Safety, and secondly, as a member of Euro NCAP. My speech is structured into three areas. I have to start with some fundamental understanding about automated driving, because when we don't have a common understanding about that, we have a high chance not to understand each other. Therefore, I have to start with this of course. Then I will show you some legal requirements and legal challenges we have to cope with when it's about automated driving. And yeah, the third part is, of course, Euro NCAP, the consumer perspective, and how Euro NCAP want to deal with automated driving. So let's start. Of course, I guess everyone here in the room know the SAE standard about vehicle automation, the 6 levels starting from 0 up to level 5, which explain the share between the driving tasks from driver only to machine only and some stages in between. I'm not that sure, something happened with my red box here, I'm not that sure that you are aware that this standard was revised already 1 year ago in September 2016. And this was very important because there was a misunderstanding in this standard about level 3. Level 3, it was mentioned in the old standards, the driver is the fallback. And some people, and also some manufacturers, understood this, that the driver is the fallback. That means immediately he has to step in when the system, the technology, the automated driving function has a problem. This was never the intention. It was always mentioned that this is with sufficient lead time. Yes, this is very important, and here the SAE made a correction or make it more clear. Now they are talking about a so-called fallback-ready user or fallback-ready driver. This is very important. This means the driver is have to be ready, and when he is not ready, the system have to deal with the issue. Another thing is, when you look into the standard itself, you will see that the basic idea is coming from BUST, by the way. 5-6 years ago, we made research on this and the SAE standard based on this. But SAE also referred to another thing, which is also important to understand. These are the operating principles. The operating principles is, in principle, an overlying structure before we're talking about the levels of automation. And here, we have, starting from the left side, the tasks a driver have to do, these 3 layers. The navigation layer, when you start a ride, you have to decide how to come from A to B. The guidance layer, this is more a tactical layer, where you decide which lane do you want to take, how to turn a curve, and then the stabilization layer, this is a concrete execution of a driving task and on a very stabilization situation. Everything we are talking today here is on the guidance layer. It is not on the navigation layer, and it's not on the stabilization layer. This is important to understand. It's on the guidance layer. And the guidance layer is structured with these principles of operation. The operation A, it's informing and warning functions. B is continuously automating. And C is temporarily intervening in accident-prone situation. When I explain this as an engineer, I always say A is not a complete circle of a controller. A is just a sensor which detects the situation, a computer which thinks about that, but then the circle is not closed with an actor. The actor is a human being. The human being is warned against a hazard, and maybe it is an abstract hazard or a concrete hazard. Maybe the human being is just informed about the status, and then the human being have to take an action. So A is not a complete controller, it's just part of a controller, and the human being is the rest of the controller. The human being have to take the action. B, operation mode C, is continuous automated. This is normal driving, and here we have our SAE levels, which explain what is the role of the human driver. And C, and this was also misunderstood by NHTSA in the first publication from them, C, here we have systems or functions which are just jumping in when it is very critical. For example, our very famous AEB systems fit into operation mode C. Of course, an automated driving have to have an automation braking, an automated braking system, and also an automating steering system, even in accident-prone situations. But the primary controller could be also a human being. So And then the driver assistance systems from operation mode C jumps in when the driver doesn't react appropriately when an accident is close. And here you see the full picture, as I already mentioned. And again, here, unfortunately, my slides are a little bit destroyed. Here you see the red is operation mode B, as I mentioned, the SRE standards. And for the blue part here, the operation mode C, we already proposed also a better or a more structured proposal how to structure all these functions which are temporarily intervening in accident-prone situations. Just important to understand what we are talking about, and this was very theoretically. We use it already in Euro NCAP, and here you see exactly that Euro NCAP also has these category A, B, and C, and I just want to give you one example here when we are looking for lane supporting systems. Lane supporting system can be based on different functions. Lane departure warning function, of course, a warning function, it's clear it must be A. I want to draw your attention on the last two functions under lateral support systems, which is a lane keeping function and an emergency lane keeping function. And we had a long discussion with industry because Euro NCAP want to have a lane keeping assist function always on. And industry said, no, no, no. A lane keeping assist maybe is not perfect on a very narrow roads with narrow curves. So it must be possible to switch it off. And then we realized with this structure in mind that we are talking about two different functions. Industry was talking about a lane keeping function which take an action in an abstract hazard, category C, abstract hazard. When there is a concrete hazard, category C, concrete hazard, this is an emergency lane keep assist, and this should be always on. So this is exactly, or this structure helped us to understand each other that we as Euro NCAP want to have this emergency lane keep assist always on. That means when there's a risk that the car run off the road, hit a tree, or run into an oncoming traffic, this must be always on. But of course, a lane keeping function which just make sure that you stay within the lanes or within the road marks. This is something different, and this could be switched off. So you see why we need these very theoretical understanding of automated driving in order to take the right action and to understand each other. A little bit about legal requirements. Here I see three areas where we have to take action or where we have challenges regarding the traffic law. And the first one is the traffic law itself, or the Road Traffic Act. The Road Traffic Act in Germany was modified this summer by the parliament. Why did we did this? The reason is we believe that an automated driving, a self-acting machine in public area on a public road is such a fundamental change that this cannot be taken by the government itself. We need a parliament decision on that. We need a parliament law, a road traffic law on this, that really the parliament is aware that we change from a car which is driven by a human being and where the human being is responsible to a machine which is acting. And this is quite fundamental, and I believe, of course, this is a national thing, and I believe every country have to cope with this, and this is not on a European level, this is in Europe and also in other regions of the world, a national thing. You have to think how to allow, from a very fundamental point of view, how to allow that a machine, a self-acting machine, can do actions in a public area, on a public road. We argue from our constitution, by the way, because the government is responsible to keep hazards away from the society, and we decide that due to our constitution, it is needed that the parliament decide about that. And just one sentence here, because many countries look to the German law and try to translate it into English, and there very often is one mistake in the translation. We have the situation that, in level 3, we are talking about the driver, who is the fallback-ready driver, fallback-ready user. And this means, again, a sufficient lead time, and it is not an immediate lead takeover, as I mentioned. And this is reflected in this Road Traffic Act as well. And here we are talking about undue delay, which is very often used, or where the translator very often use immediately. Immediately is wrong here. It is the legal term undue delay, which means, or which reflect these sufficient lead time for a human being to step in back when he is a fallback-ready user. And again, this is a national thing, and every country have to think about how to modify your road traffic law. The second thing is about liability and insurance. In Germany, we have the lucky situation that our vehicle insurance based on two pillars. On the driver pillar, driver means the driver is insured when he or she makes a mistake, so a fault-based liability. But we have also a second pillar, which is the vehicle keeper insurance. And this is just because of the operational hazard of a vehicle in the traffic, independent if there is a fault or not. And this is a lucky thing that with this second pillar, we can allow immediately automated cars on German roads because they are already insured by our system. But this, again, can be different in different countries. And in Europe, we have big differences. Again, this is a question how to cope with this. And the third one is, of course, the technical thing, the type approval. And here we are on an international level, which is the UN Regulation 79. You know that the ACSF group tried to modify or create criteria for an automatically commanded steering function, which is more or less an automated driving. Okay, last 4 minutes, consumer perspective. As you have seen in our roadmap, Euro NCAP wants to deal with this question of automated driving. And the first question is, in which way? So it is, again, Euro NCAP will focus on continuously automated driving. This is this category B we already learned. So it is normal driving. It is not accident-prone situation, because all the functions from accident-prone situations, the category C functions, are already in our standard safety assessment. Now we are looking for normal driving. And due to the fact that automated driving is seen separately by the consumer, and we don't want to compromise our very well-established 5-star current rating system for safety in a car, we decide to have a separate rating, or at the first stage, grading for automated driving systems. Question is, how can automated driving contribute to road safety? And I see two sources how automated driving can contribute to road safety. It is the avoidance of critical situation. When the car is driving in the given use case, the car will always stick to the rules. The car will not speeding, the car will not be aggressive, the car will not be distracted. So the absence of critical situation is one main contributor to road safety, but at the beginning, the use cases are quite small, that the car can be self-driving in a parking area will not create many benefit for the society. But we cannot imagine, and this is the second source, we cannot imagine an automated or self-driving car with all these emergency functions from C. And this is the main contributor at the beginning, in the first years, because these category C functions can be also always on when a human driver is driving without or in an area which is not covered by the use case of the automated driving function. Therefore, again, this is the main focus for us, category C functions in automated cars. Yes, what is the objective? As always, and as in our 5-star rating is the same, the objective is on one side to establish good, high standard criteria for continuously automated driving functions. And on the second, it is the information of the consumer, an independent information of the consumer. What the consumer can expect from a car, and what is his role in a car which is automated, which called whatever, autopilot, and what is his role in a car which calls this automated function autopilot. And yes, we have to transfer a very complex situation, as you have seen at the beginning of my presentation, into a very simple message to the consumer. And we decide already that we will use these 4 steps, these 4, I don't want to say levels, we say grading scales. It is continuously assisted, basic automated, advanced automated, and superior automated. And the expert already realized that continuously assisted is level 2. And the basic, advanced, and superior automated is level 3 or higher. As I said, we start the assessment with the use cases. So we look into the handbook and look how the use case is described, and we decide we start from level 2 up onwards. That means level 2, 3, 4, or 5 systems. And of course, we look for the use case, and we look how the use case is described. And then maybe this is one use case, a second use case. So we can imagine many, many different use cases: a highway driving, a pilot, a traffic jam assist, a parking assist. By the way, traffic jam assist, traffic jam pilot, this will be soon available on German Autobahn. As you have seen, our traffic law has changed. It is allowed to turn away from the driving task under the new German traffic law regime, and Audi with the A8 will bring an traffic jam pilot soon onto the market. So this will be the first time that ordinary people, normal people, can use it. The assessment is grouped into 2 things: system performance, the technical performance, and on the second hand, the HMI, the human factors assessment with the mental model, with the mode awareness of the driver. So we will explore new areas of assessment with the methods from the psychologists. And we have 2 subgroups, human factor subgroup and the testing subgroup, and industry is invited, and I don't want to show the picture now, the film now. Last sentence, Euro NCAP, yeah, sorry, you have to blame Anders. No, you have to blame me, I'm a little bit too long. Last slide is we will do a phase-in approach. That means we start with level 2, which is available at the moment already, and we hope to be able to communicate within the year 2018 with the first assessment of automated driving functions, and we will continue this for the next years and maybe for a long time. Thank you very much for your attention.
Thank you, Andre. This already gives you a bit of an idea what technology innovation means for regulators and also for consumer organizations like ourselves. It's quite a challenge to deal with these systems because actually all the definitions that we used to know have to be redefined, re-reviewed. The next speaker, I'm really pleased to announce, we go from Germany to North America, to the United States. I think one of the areas in the world where automated vehicle technology and also the policy making is perhaps most advanced. I'm very pleased to introduce Brian Reimer. He is a research scientist at the MIT H Lab and the Associate Director of the New England University Transportation Center at MIT. His research, and that's a mouthful, seeks to develop theoretical and applied insight into the driver behavior by fusing together traditional physiological methods with big data analytics in computer vision, deep learning, and predictive modeling. So he founded and leads 3 academic industry partnerships, including the AVT Consortium, which stands for Advanced Vehicle Technology, focused on developing understanding of driver use of emerging vehicle technologies, including production-level automated driving systems. So it's, I think, the ultimate perfect person to talk to us about advanced technology. Please.
So I come to you from the smaller of the 2 schools in Cambridge, Massachusetts, the one where technology is in the name. Now what's your question? And I come to tell you that perhaps technology evolution is not going to solve the future of driving in the ways that many would like to predict. 90+% of accidents relate to human behavior. And as long as we, as humans, are a core component of vehicle transport and have a role in the system, whether that is a supervisor or active driver, we have a responsibility to consider how the human may relate to this complex social technical system. Well, the context of vehicle automation is discussed on a daily basis as being new. Well, we have 5 or 6 levels of vehicle automation. The context of automation, however, has been going on for decades in the automotive ecosystem. Perhaps for me, the tipping point in vehicle automation in the car has nothing to do with Tesla's autopilot system, Audi's A8 that comes to market soon, or even Google's self-driving car. The tipping point is the introduction of the automatic transmission. So moving my hand from shifting, I'm an American driver, so it's the right hand, from shifting to an automatic transmission, automation, reduced my responsibilities. What do humans in the US, drivers in the US do? They picked up the phone. The relationship between automation, reducing workload, and human behavior is what? We find something else to do. So, class participation here is 95%. If we reduce the human's responsibility through automation, what's the human going to do? Find something that we don't fully understand yet to do. Even us technological folks believe we know the answers. Humans will find another reason. Or as we were talking about, Apple will invent something new for us to find to do that we haven't even envisioned yet. So when we think about advanced technologies in the car, I have the pleasure of leading an organization that's supported by Delphi, Liberty Mutual, JLR, Autoliv, Toyota, Giro, and Consumer Reports, and I welcome many of the rest of you in the organization to get involved here, to begin to look beyond the technology, to look at how technology interacts with humans and the environment in real-world situations to begin to understand how people are using, leveraging, or not using technology in the wild. So while we as engineers love to build technology in the lab, build specifications, think about how do we engineer to the best possible specification we can define, when we get into the chaotic, wild, real world, people do impractical things. We experience edge cases, situations that no one would expect. They're not practical. By all means, that's because we're only human. So our focus here is to collect data, to begin to characterize an understanding, particularly in the L2 area, how people are using automation in the wild. Now, this slide was formed on the last data set poll we had, where we had about 150,000 miles of data on disk, and right now I'll tell you it's somewhere closer to 250,000 miles on disk. Or about 200,000 miles of that data is watching drivers in Tesla vehicles with autopilot. And everybody would say, well, it's the video, it's the amount of miles that are of interest. Lots of folks in here will tell you it's not the miles, it's the frames and the pixels of information that begin to characterize the information content in the new world currency video. So when we begin to think about these technologies and we begin to educate some of the consumers we're working with around technologies, one thing becomes very salient. Even in an educated or trained user, terminology around technology is fatally flawed. So if you train somebody and you teach them about adaptive cruise control, yes, the bulk of your population remembers the word adaptive cruise control, but you're filtering cruise control, forward control maintenance, lots of other funny words. So when we think about the terminology of technology, we need to think about education. Someone earlier on this morning mentioned the dealership and the delivery of technology at the dealership, and I could go on for a half an hour on how problematic that is in the US. If we want to move advanced technology to the consumer, we have to train the consumer and teach them how to use it. The myth about automation is, with automation and technology, we can rely on less human expertise. It's a myth. We need to educate more. So when we look at technology in the wild, everybody sits here and thinks, well, Tesla's leading the way by doing automatic updates from the cloud. Well, you know what? Volvo did a dealer deliver update in the US this spring, where they significantly improved the performance characteristics, here measured as the percentage time available of the pilot assist system, substantially. But when you went to the dealer and you took your car to the dealer and they installed this upgrade, they handed you a little pamphlet. And they told you about the upgrades to the HMI for the navigation system. They didn't tell you that, number one, they turned off the lane departure warnings and they're relying solely on the haptic systems, or two, they altered the performance characteristics of their quote-unquote cutting-edge automation system. So a user, if someone was to use the system and had the experience, gets into the car, starts driving it with it again, and the system's fundamentally behaving differently. So from a responsibility and ethical perspective, if we are going to change technology, and I hope we do set a trend moving forward of improving technology over time, post-production, we need to be clear and transparent to the consumer in that. And we already begin to see cases today, from Tesla, where you get a nice little README, to Volvo providing perhaps incomplete information at the dealer. When we look at Tesla's autopilot system, what becomes very painfully obvious in a very positive way is over 30% of the miles and 10% of the time that drivers in our study are involved, and this is over 20 individuals, over 200,000 miles, about 30% of the miles are being traveled under autopilot. In essence, drivers are using this system to a large degree in highway fast travel conditions. What other driving assistance technology is there out there that is being used in the US marketplace for 30% of the miles traveled? Now, what's interesting when you begin to look at those miles, and you can look at the plot on the right here, the blue GPS points are where the autopilot system is engaged, overlaid over the red GPS points where manual control is interacting. You see that, look, it's highway travel. That's great. Okay? That means people are by and large self-selecting the geofence themselves, which is good. Okay? Why isn't there a geofence involved here? That's a whole other question, a strong geofence. But what we do see among the 16,000 transitions of control in this system, over 450 hours of use, that we begin to see that humans are by and large turning the system on for very short periods of time on occasion. In other cases, an extremely long tail where usage in the half-hour range is not uncommon. So drivers turn the system on, and we'll call that human-to-machine transition, and drivers turn this off, machine-to-human, human-initiated transitions, where the human decided that for some reason I don't feel comfortable with this system, I want to get off an exit or for any other reason that we may think of to turn the technology off. Then there's a third class here, the class being the system initiating the transition. Out of 450 hours of driving, there's 42 of them. 42 situations where the vehicle said, here, driver, it's your problem. And that sounds like a lot until you dive into the numbers a little bit. 12 of those cases are the driver exceeding the ODD speed boundary of 90 miles per hour. Is that carelessness? The system was only designed to work up to 90 miles an hour. Another subset, following a car through an intersection, hands on the wheel, trial and error, experiential learning. How far can I push this system? We never really taught them how to use it. So when we look at autopilot, for all of its flaws, it's perhaps one of the most successful, if not the most successful, human-robotic interaction that has been created to date. Humans are interacting with, for some unforeseen way, quite successfully with a highly complex robotic system. And perhaps by luck, that is based upon the fact that it is flawed just enough that the human does not overtrust it in most situations, but good enough that we're willing to rely on it to some degree. The interesting questions will become, over time, as we understand safety over billions of miles, does it advance safety, as Elon Musk would like to proclaim, or does it become more of a safety nuance over time? And that is something we'll all figure out together. So one of the big interesting questions that when you begin to look at naturalistic data is that the relationship between our theoretical understanding of automation and what actually happens in the real world gets very mushy. For instance, let's ask the question, when has the driver successfully accepted the transition of control? When have they regained full awareness of the operating scene? Further, drivers demonstrate a variety of different use styles. So the concept of a lot of the theory we've been developing in the laboratory and building simulations around needs to be validated to real-world use cases to understand which aspects of the theory carry over and which aspects don't. We can also begin to use the data that we have to train end-to-end deep neural networks for perception and control. That means relying on the pixels of information to develop steering control. In this illustration here, the black wheel being Tesla's proprietary control system, the green wheel being our end-to-end network laid on top of that. What we can do is look at the divergence function in the bottom right, and using that divergent function, we can train a classifier to predict with 90% accuracy in a 6-second window the likelihood of a human to decide to regain control from the autopilot system. In essence, something salient is occurring in the scene and the world ahead of us that the classifiers are detecting. We can also use a different form of deep neural networks, deep reinforcement-based learning, to develop a perceptual control system where the robot here, in the form of an RC car, begins to learn from experience how to avoid high-speed crashes. So being trained by experience of crashing, how to learn not to crash. So for those of us in the world of automobile crashes, if we had the video from 250 million crashes, can we use AI and the advances of AI to teach a robot how to avoid unpredictable crashes as we see them today? And from a theoretical perspective, at this point, the answer appears yes. Thinking further, another flavor of my work. Developing an integrated model of driver attention. As I mentioned at the start of this talk, as we automate, we reduce driver workload. I was given a clean slate a number of years ago and currently working with Denso, Honda, JLR, Panasonic, and Google to really move and develop a new philosophy on how we think about HMI design. To say, is the perspective on driver distraction that has been center point to the automotive industry and the regulatory frameworks for a number of years the right perspective? Or do we need to begin thinking differently under the context of attention management on how to deal with high levels of demand, fatigue, and attention all together in a ubiquitous framework as a whole, with the growing trend of risk on the road from distraction, manual driving, and automation? Context, how do we help the driver in real time make better decisions? To give you a quick flavor, how we begin to do this, we begin to think about the context of driver state estimation. Topics such as body position, gaze region estimation, emotion detection, cognitive load estimation, hand placement, and perhaps even the most important to some of us, smartphone detection in the vehicle. We can use computer vision, deep learning, and other vision perspectives to understand what's happening in the cab of the car in ways that are not trivial, but are quite practical today. The illustration on the right is an image processing pipeline for cognitive load detection, where we can pull levels of cognitive load out of naturalistic data in 3 levels and accuracy over 86%. And in real-world data, that is a number that is, by golly, approaching the ceiling. We can begin to think about the perspective of distraction quite differently from attention management. Distraction says, hey, I got a crash. What happened before that crash? Hey, the dummy was looking at the phone. Great. What can I do about that? Absolutely nothing. But from an attention management perspective, what is drivers doing upstream that led to the downstream consequences of looking at that phone? And is precisely what is happening upstream that perhaps is leading to that inopportune glance at the wrong time. So from an attention management perspective, we want to say, how do we manage the flow of information over time? The criticality being acquiring information by looking at the road. For those of you who do HMI assessment, demand assessment, everybody's been trying to minimize the off-road glance time. Well, what do we want to do at the same time? Maximize the threading of glance time at the road. And that has been, for better or for worse, because of some policy and funding decisions over the last 15, 20 years, ignored. And it's precisely in the relationship between on-road glance time and off-road glance time that lets us build curves like these. The hybrid measure of attention that we've developed allows us to see divergences in the attentional profile of crashes from near crashes in the 100-car naturalistic data set in the US, approximately 15 seconds prior to the precipitating event. That's way out there. What can you do with 10 or 15 seconds of information? I see Michael saying, I can do a lot with that. Better yet, it validates from the SHARP2 data set, which means it wasn't a one-of-a-kind finding. And when you take aspects of the SHARP2 data set apart, perhaps in the illustration on the right, texting, and you normalize to the phone interaction, you say 0% to 100%. The curve on the right shows us that the individuals who ended up in a crash started texting with depleted awareness to the outside world. That means it's not about the texting task in itself, it's about the inopportune time that they decided to text. So we've been worried for decades about how do we ensure designing better HMI, minimizing the distraction of an interface. And I don't want to say we want to forget about that. Perhaps the bigger overarching question is, how do we help drivers choreograph the information flow over time and make better decisions when they begin to integrate and do things in real time? That means adaptive HMI and adaptive automation, all brought together under one umbrella. So some closing thoughts. The future may be autonomous, but humans will have a role for some time. Level 2 systems introduce a number of use challenges that are incredibly interesting to study and explore, and many of us are doing that now, and we will continue to do so for decades to come. Reported experiences with L2 and L1 technologies combined with qualitative data tell us a story, and I wish I had time to talk about the story in depth. But the story is one of mode confusion, role confusion, and system confusion being the taxonomy. Role confusion, or mode confusion, what mode is operating now, role confusion, what's my responsibility, and system confusion, what system's trying to help me? What do we have on the roads today? An utterly confused, uneducated driver. But we're creating higher levels of technology to go along with it. So investment in human-centered engineering throughout the automotive ecosystem is really critical to safe mobility. If we don't include the human in this decision process, whether we're developing L1, L2, L3, or L4 vehicles as a centerpiece, we're not going to solve the problem we want. That means improved communication with the driver, fuse decision models that consider driver state, and consumer education, whether that's dealer delivery or in pseudo. Only if we can get the policy, the technology, and the human factors to overlap can we really solve the automated driving questions that we look to achieve. Solving any one of these buckets alone will not make the safety changes we need. They have to work together. So for those companies out there that say, we're going to create the technology that's going to change the world, it's only going to change the world if the human and the policy goes along with that. So in terms of NCAP, looking forward for the next 20 years, NCAP's going to need to consider some things that are quite different than the past. One, technology enhancements post-production. How do you revalidate a safety system or a crash system when a car was updated 6 months after it was released? How do we deal with active learning systems? Systems that are learning minute by minute. Tesla's got a great example. Autopilot is learning day by day and updating the decision models. Is that good or bad? Hopefully good. Automation that changes how we view harm. the whole context of harm, fatalities, injuries, property damage, safety, environmental impacts mentioned earlier, we need to rethink about that. Is it sum zero or is it some derivative of sum zero? Consideration of safety from various perspectives and benefit estimation. I believe in societal considerations. If you can cut the number of fatalities in half, that is an achievement to my perspective. But from the engineering side, the manufacturers will look at that from a safety liability trade-off, and the user at the end of the day, did you protect me? It's all about me. So, a few in the audience are from the biomechanical world. New cars will maintain their form factor for some time. But changes will appear that could justify the elimination of the steering wheel, the throttle, the brake, some of today's passive safety systems, and perhaps even at some point, traditionally manually controlled vehicles in some contexts. However, I will tell you, you have a lot of interesting work to do because the same automation technologies are going to drastically change how cars collide, how we need to protect occupants in the future. This is not going to be a transformation to zero overnight. Only if the industry works together with the policy and the quasi-governmental regulation organizations and academia together will we actually be able to achieve the vision zero that we all strive to. The complexities of automation are immense, and they have enormous potential. And it's going to be a fun road for the next 20 years of Euro NCAP and the rest of the safety community. Thank you all for hosting me. If you have any questions, feel free to send me an email. Thank you.
Thank you very much. It's a very inspiring cultural journey we're doing. We see different cultures and different approaches. And we will now continue that journey to Japan, when Tetsuya Iijima, who is the general manager of automated cars and driving at Nissan Motor Company, will present on the theme, bringing autonomous drive to market, technological challenges and solutions. Please.
Hello, everyone. Thank you for inviting us to this stage. Today, I will talk about Nissan's recent approach, how we introduce real autonomous driving technology onto the market as fast as possible and as realistic as possible. First, I'm talking about our milestones, how we introduced our technologies. 2016, highway single lane technology. This is the first step. And second step, 2018, highway multi-lane technology. And 2020, including urban roads and intersections. And mid-2020s, free autonomous drive and driverless technology. We think step-by-step introduction of this technology is critically important to let drivers and society to have a better understanding and better acceptance of the technology. This figure shows what kind of aspect is the most critical at this moment. We believe expansion of the available situations is the most important as of today. And innovation in environmental perception is a key to realize this part. So the enabling technology is sensors or HD map or V2X communications. Next, we are talking about ADAS. AD technology comes from the first asset of the ADAS. In Nissan case, we are aggressively working on this technology in the past 18 to 19 years, and we have many industry-first technologies. For example, for longitudinal technologies, in addition to AV, we have what we call distance control assist. This is a combined technology of automated braking and force feedback pedal that works always without ACC activation. And for backward, we have what we call backup collision intervention. This is the automated braking function to avoid the collision with the cross traffic and rear crossing pedestrians. And for lateral part, we introduced lane departure prevention and blind spot intervention for our name. This is the combination of the radar sensing technology and braking control technology. And for surrounding view enhancement, we have a around view monitor with moving object detection. This is not only a vision information, but also the integration of the machine vision and the surround view display technology. And in addition of ADAS technology, we need to add the advancement in other technologies, like reliability. Reliability, in this case, in a very general meaning from the customer concept point of view, and redundancy of the system, and HMI for safety. These are the main area we need to stress, we need to focus to introduce AD technologies. From here, I want to explain about some of the important part of our three technologies. First, reliability. This is the very general concept of the customer. So how far the system is available in advanced environment, or how far the system is capable to react to the critical situations. Advanced environment, rain, snow, fog, sandstorm, these are very easy cases. And critical situations, most typical case is a sudden movement of the adjacent vehicle. This is maybe one of the most critical situations driver need to react in emergency. And it's a rare case, but for example, the vehicle jumps onto your vehicle over center divider. This is the actual accident that happened in May in Japan. And landslide, this is also the sudden situation. So to enhance the capability to react to these situations, technology enabler is a sensor system, algorithm, and vehicle response. The next, I'm talking about the redundancy. Redundancy is required to secure safety in failure. And there are 5 areas of technology. The first, sensing. More than 2 sensors should detect one object. And for control algorithms should be located in backup issue. And for actuation, 2 ways of actuation need to be equipped to maintain steering and braking function in case. And for communication, dual communication bus is secured. And power supply, dual power supply network need to be secured. These are the design requirements for redundancy. But in future, we need to have a more strict requirement for this area. And next, HMI for safety. This means before complete replacement of the human driver is attained, driver need to provide a proper involvement in the driving. So system must be designed to secure proper involvement of the driver, and it's mostly warning. And so if the system thinks driver's involvement necessary, system need to issue warning using a display, sound, or haptic with an intuitive way. But in addition, if driver is not available, the vehicle needs to stop safely. These are requirements for HMI for safety. So we understand how to design important, essential part of the autonomous drive designs. And the next step, if we want to accelerate the development of the technology, we need to understand the real traffic environment. Traffic environment are mostly categorized in two areas, road structure and traffics. And if we see the different technology for highway use or city road, or the road structure and traffic is very different. For example, for highway, comparatively simple structure. However, in city road, intersection or roundabout is very complicated. And for traffic on freeway, only motor vehicles and the situations are mostly predictable. However, on city roads, vulnerable road users exist and situations are very unpredictable. And in addition, road structure and traffic safety is different in different geographic regions. So we are aggressively accelerating the test on public road. We have already conducted intensive evaluation of this technology in Silicon Valley, London, and Tokyo in the past 2 years. The vehicle we used in each region, this is a sensor set for the vehicle. So 5 radars, 12 cameras, and 5 radars are installed to detect the various traffic situations, like a right turn or traffic circle or angled intersection. And this vehicle also have a specially designed HMI. And the several display mode is provided, provides intuitive understanding of the system status in different environment. For example, speed dependent view. At low speed, the system screen showed the forward object. But according to the rate of the speed, the eye point gradually go higher and the display showed the more wide area of the vehicle. This is consistent with the driver's interest in each situation. And in addition, we have a city driving view. So driver is concerned if the vehicle is correctly understand the situations. So we will show the roundabout view because the traffic and road environment are very complex in this area. And for in residential area, we will provide a specially designed fine view because the some area is restricted to drive, and some areas pedestrian crossing exists, and parked vehicle also appears. And in the right screen of this picture showed the some special rules in England. In England, if the pedestrian is waiting under this yellow ball, vehicle must stop. This is a very strict rule. So this screen showed the system understand the strict rule correctly, and you need to rely on the system. And next, so based on our past evaluation in 3 regions, we identified various situations that need to be investigated more in detail for road intersections, various intersections, roundabout, lane reduction, traffic signal local rule, zebra zone, vehicle should not stop in there, and freeway exit, merging tunnels, and traffic, pedestrians, bicycles, parked vehicle, crossing vehicle, stop vehicle, cutting in short distance. These stations are precisely analyzed and reflected to the next version of the software. Now, I can show you some of the footage of our test driving. This is a Tokyo downtown area and driving in a typical downtown scene. this is a bridge on Tokyo Bay, and we are doing the auto lane change in here. This is under the tunnel. GPS signal is not available, and this is merging in dense city traffic. And this is a typical downtown driving area, including intersection driving. And then this is the Silicon Valley test. We are now driving 101 on freeway, and also driving on the city traffic, including intersection and signals. And this is very critical merging on freeway. And then this is the left turn, identifying the arrow signal, and need to drive where no lane divider is provided. And this is the London test, close to London City Airport, east side of the London. And driving traffic circle. And the lane divider is a special shape, and signalized traffic circle. And the screen shows the road structure of the traffic circle. And now we are driving onto the residential area where there is a restricted area in the center of the road, or parked vehicle, or pedestrians, or crossing information. And actually, in here, pedestrian is walking on the roadside. So precise location need to be shown on the display to make a good trust between the driver and the vehicle. So this is the typical driving scenario we challenged in the last London demonstration. And then we look back upon the milestones of our technology. Now we are in 2016, 17, and last year we introduced a highway single lane technology from a Japanese market. We already introduced 3 models, Serena, this is a Japanese dedicated model, and X-Trail, and Leaf, this is a new Leaf, just last week. And we already conducted some customer acceptance, and 97% of the customer use the system on freeway because it's very easy to use and reliable. And 69% of the customer have a positive driving impression. This is a very encouraging for us to expand this technology to mass market. And then for the next stage, we are focusing on the development of a highway multi-lane technology and urban road intersection technology. Thank you very much.
Thank you, Mr. Ijima.
Yes.
I think a very clear example how mainstream manufacturers, volume manufacturers, are ready to deploy this technology onto our roads. We move on to the next speaker, which probably doesn't need much introduction as he was on stage already, Ola Bostrom from Autoliv. You know, everybody knows Autoliv as a company with a very long history on passive safety, recently also into active safety, and I think from last year on was propelled into the area of automated driving with their cooperation, Zenuity with Volvo. You're going to talk about a bit of everything, I think, from the passive safety perspective as well as from a sensor and communication perspective. So the floor is yours.
Thank you very
Thanks,
much,
Ola.
Michel. So, the title here is On the Road to Saving Lives. That's what I'm going to talk about. And with sort of passive and active restraints, with ADAS and AD, and AI and user experience. So I would like to start talking about levels of trust, shifting from discussing levels of automation. So start with confidence and trust, two various aspects of trust, where basically confidence is built on experience and trust is not. I will come back to that. And when I talk about trust or confidence, bear in mind, I'm not referring to when you over-trust or under. You see the examples there. Well, if you trust the car for some reason, you can text while driving. That's an over-trusting. And if you switch off safety-critical systems, that's also under-trusting. We believe that we need to build trust in order to save lives, and I will come back to reasons for that later. But what I mean with this is to have a consistent user experience. And I think, as we heard this morning and this afternoon, I believe that this is something that Euro NCAP can do a lot of thing about, to make the experience consistent. It's also managing the mobility and to introduce and use sort of the new breakthroughs in deep learning and machine learning. In our company, we put a lot of emphasis on that right now, and we have to bring this in. And I will come back to that. What we build trust from is what we do already in everyday traffic. So this is sort of the quality, the robustness, and innovation. That's sort of what we do as the platform, what we do today, where we produce airbags and belts and radars and cameras all over the world, every day. They should work in every day. So it's about bringing this together, and I will talk about that. Another view on the roadmap to save lives could be this. You take your hands off, feet off, your hands off, and eventually the mind off. We don't believe that this is sort of the true roadmap to save lives, to get rid of the driver. And I will sort of steer away from that and still talk about automated driving. On the other hand, we have a lot of data coming in our new cars. There are a lot of sensors out there. We get a lot of information, but we don't use it. There's not much of this data being used. And as we heard Brian was talking about for the drivers get less and less experienced getting supported from the car. And you can hear stories about that. People going from a car with a blind spot detection, not understanding really that blind spot helping them to avoid a crash. And then they go to a car without blind spots. And then all of a sudden they realize something is missing there and they almost crash. You hear these stories. So, to put it simple, we need a human-centric approach. And that was what Brian was talking about here as well. We need the human and the machine as a joint cognitive system. What I mean with that is, if I sit in the car and look straight ahead, the car can look rearward as a joint cognitive system. We can have a shared control, transparent, clear way how to share the control in the car. Some tasks I'm still doing as the driver. Some tasks is done by the car. And to accomplish this, we need the car and the driver to trust each other, both ways. Otherwise, it's going to be switched off or it will not help. And then that's the reason why you have the user experience and the deep learning there to the right. We need to bring that in. At least as for us as a supplier in this business, we need to really get that competence and supply in this area.
Hi, Katie.
So that was the Learning Intelligent Vehicle. We launched it in January this year, a research vehicle to show what we meant with the human-centric approach, with shared control, bringing AI and user experience together. So we had a live vehicle you could drive on a parking lot in Vegas and experience what we meant. And we got a lot of good feedback from that. And we are continuing working on the Live 2.0 for next CES and using it as a research vehicle. So let me talk about the road towards what we believe would really save more lives. So you see two axes here. One is the real life safety. That's where we've been we feel safe within our company to produce quality and robust products. And as I've been talking now about, it's not enough. You need to consider the user experience, getting the trust in there. And here I put up 4 stages, and I will talk about them. The cool stage, the confident, the intelligent, and then the trusted level. And the Live car is sort of showing at least the intelligent stage. So what I mean here with cool stage is sort of the willingness to buy. It's about reacting and responding. It's basically the basic ADAS. When we will gain understanding by the usage of these products in this stage. And people want to buy it. Again, blind spot. People do want to have blind spot in their next car if they tried it. This is something we can see in research. The next stage is the confident. It's about plan and monitor. Less warnings, more pleasure. People switch off less times. And we can call it advanced ADAS. And I will come back to, we're going to do some safety benefit calculations out of this. So far, this goes almost on itself. Now we come to the sort of the more trickier, and we come to the intelligent part, where we're talking about behave and learn, and the car is as good as an alert driver. The car is as good as an alert driver. And the user will regard the car as intelligent, and that is the theme here. And the last one, trusted. It's about anticipate and model. So the car can handle completely new conditions. That's basically level 4 and 5, right? The user can fully trust the car to drive and still drive it. Now, in the bottom line here, should be on the top maybe, is that for all these stages, there's airbags in the cars, belts, and they are used. And that is extremely important for the benefit calculations I will now show. So in all these stages, think of bags and belts according to new seating positions and new loading conditions. So let's calculate what this means in terms of saved lives, okay? What matters here? So the method we're using is used before, for example, by Johan Strandroth. So basically, we take 3 in-depth databases. One from India, RASI, one from Germany, GDAS, and then NAS. Okay? We start there. And then we put up some bundles here. So we put up the airbags and the belts, the standard ADAS, for example, in the first stage. And then we apply rule sets per this technology. So we use risk curves, we use sort of to what speeds you can anticipate the function work, etc., etc., etc. Okay? And then we calculate the residual. So what's left from today traffic, from India, Germany, and US. And then we extrapolate to future levels. And that is basically then the way we can calculate the benefit, taking from these 3 countries, which sort of represent from low to middle to high income countries. So you're the first one to see this publicly. This work will be published the year to come in more than 1 paper. So you will have time to read the details, and we can sort of redo these calculations in many ways. But to start with, we start with 1.4 million fatalities per year. That's the starting point, 2015. And if we do nothing meaning we don't do any research, we don't have these type of workshops, and we just live what we have with people in China not using the seat belts, airbags not in all cars, and the standard ADAS only sort of survives in a small fleet. We go up to, I would say, 2.4 million, 2045. On the other hand, if we bundle together the cool stage and the confident stage to one stage, we call it confident. So imagine until from now to 2045 in these cars, you have today's safety technology. Consumers apparently want to buy this, and confidence in the vehicle's perception. Then we will see this. So basically, you will sort of stabilize the situation. We will have slightly more than 1.4 millions, 2045. Again, according to these calculations. If we take the other 2, the last 2 stages, the intelligent and the trust, and we call it trust, we see quite a good lives saved calculation here. So imagine 2045, all cars having some sort of co-pilot, shared control. The driver considers the vehicle intelligent, and there's a full trust in the vehicle. Basically, the numbers will go down to close to 0. So how, as a supplier, how do we tackle this? So we're using this pyramid. It's very hard to see what it says, but on the bottom here you have the LiDARs and the radars and so forth, and then comes the blind spot monitoring, and then you go up and you get the lane keeping, and then you go up, you have the AEB, and then the more you come up here, you come closer to autonomous driving. And we really started from the base here. That's sort of where we come from with quality and robustness and provide these sensors. And then we formed the company Zenuity this year, together with an OEM. So the Zenuity is sort of taking part of the upper part of the pyramid and focus a lot of deep learning. Now, we have joined forces with OEM, but there's no exclusivity at all involved. So we can provide software to any OEM. It doesn't have anything to do with our joint ownership of this company. Okay, sorry. I just introduced this movie first. So imagine now in a movie, and again, this is the first time publicly it's shown, okay? So you're the first viewers. Imagine sort of a future of automated driving and how we combine active and passive safety. So enjoy. So don't consider this as sort of the solution. It's not about that. It's just to show you that if a OEM says you can recline the seat and you can trust the car, you can sleep, then you may need a belt system. The belt was integrated in the seat here. You need an airbag system that provides you with support in this crash. You're not helped by a curtain up in the roof. You need it closer to. So regard what you just saw as how we see sort of how we need to comply with new load conditions, new seating conditions. So my concluding slide here is one word here that comes into my mind at least for what I've been talking about, and that's collaboration. Collaboration between the driver and the car, not elimination of the driver, which is sometimes sort of discussed, but a collaboration. And when I bring this up, it's not just development I'm talking about or producing. It's putting research money to understand how do you collaborate within a machine and a human, not necessarily in automotive, and to understand from other research fields as well. The other collaboration theme is between active and passive safety. Clearly, as I showed now in this video. And at last, collaboration across organizations, between suppliers, OEMs, universities, NCAPs, and so forth. Thank you for listening.
Thank you, Ola, giving a Swedish touch to presentations, and there are some very interesting findings, I think. We continue the program. We are now at Eris Dagan from Mobileye, who will present provably safe and scalable AV architecture. Please welcome to the scene.
Okay, so good afternoon. Thanks a lot for having me talk on this event. I want to, here we are. I want to correspond just shortly before we start with the talks that were given so far. I think the triangle is very important to visualize the policymakers, the human, and the technology. And I see that the previous talks gave very firm and very valid points about the human and technology interaction. I would like to focus on how we improve the policy-technology interaction such that we can maybe even assist that other link of human and technology. I think that the policy should always represent the best interest of the public and of that human, so maybe that's another way of building such trust. Maybe just to be, I'll start with one very simple, very true and naive and banal statement that autonomous driving carries a promise of huge public safety and societal efficiency benefits. And these are two different things. Public safety is one thing, and that's the motivation of this organization. Societal efficiency is another word for economy, of like a dirty money word that we're talking about, but it's the immense economical benefits in autonomous driving are, we cannot ignore them. What you see here screen, and we'll see that video again later, is an autonomous driving demonstration in the last CES in Vegas. The important point, and here is the less straightforward statement to make, is that sustainable AD solutions must be provably safe. It's not just safe. You need to be able to explain why they're safe. And that's, I think, where most technology suppliers are now standing. It's not making the technology safe, it's being able to demonstrate its safety, predict its safety, both to the policymakers as well as to the humans that are going to use it. And that's a big hurdle. And the other thing is, if we want to collect the other fruit of societal efficiency benefits, we cannot violate the economic scalability of these solutions. We need to have them economically scalable, not deal with brute force technological solutions if we want to also benefit from the other economical aspect of it. So the few upcoming slides, I'm going to rush maybe through some of them because they lay the technical foundation for what we want to say. But if I want to give some sort of motivation for these slides, it's that misdirected approaches to the problem may risk widespread adoption of AV into the future. If autonomous driving will increase the level of fatality before it decreases it, it will be shelved for many years. And we have to conduct responsibly in this introduction phase. And lack of formal model-based safety assurances may lead to rely on intractable empirical safety validation techniques. That's a long sentence. Another way of saying is that if you don't have a formal model of why your car is safe, or a formal model that structures your approach to the safety of the vehicle, out of the box, or treating it as a black box and only empirically validating it, is not a very good strategy to do. It's not a tractable one. The second part is that, again, ungraceful scaling in terms of economies of the solutions could also be a hurdle to the widespread adoptions of these solutions. So again, the next few slides are going to be a bit textual, laying the foundations, and then we get back to the fun video just to see the technology that implements it, okay? But bear with me, please. I'll try to make it a bit short. We're going to show a pragmatic and applicable formal safety model and share Mobileye autonomous vehicle design principles and the formal safety and scalability aspects these principles adhere to, okay? So this is basically our work in this, and this is our map for the entire talk. So understanding this map will allow me to run through the more boring sections of it. Let's look at sensing and driving policy. Policy here is not in the sense of public policy, it's in the sense of driving policy, decision-making of the vehicle. So we have two technological layers: sensing of the environment around us and making decisions in light of our perception of that environment. That's sensing and policy. The the vertical columns stand for challenges in terms of safety and scalability of these layers of the solution. As mentioned, for the driving policy safety, we present an RSS model. The innovative approach of that model is that it clearly and formally captures the concept of blame. Okay? I think that in any engagement of humans running into an accident, that's a key aspect, a key question to answer. The important and the responsible statement to make is that we cannot guarantee 100% safety. We can guarantee 100% safety up to blame, up to the responsibility of that autonomous vehicle. And we can easily visualize a situation where a vehicle is driving in between a few cars, unable to change its position, unable to take any evasive maneuver, and one of the other vehicles simply runs into it. And we really need to very out loud spell this blame or responsibility very, very formally, so we can then guarantee safety. Moving downwards, we need to understand the implications of sensing systems and decouple the implications of these sensing system errors on safety critical elements versus drive comfort. These are very, very deeply different aspects of autonomous driving. And this distinction allows to also move us into more scalable and pragmatic AV solutions as we go forward. But we use the RSS model of the decision making to formally infer a clear distinction between sensing errors that cause safety problems and sensing errors that cause mere comfort problems. And this is a very important distinction to make. Let's move, for the other ones, I think that the block on the right, lower right side, that's where all the fun videos are. We'll see it, it's all of the technology and what we propose as a scalable solution to the problem. And on the policy side, we also propose a scalable decision-making solution. Something that does not, let's talk about it just for a second. The technological challenge of decision-making in a very dynamic environment is if you take that computational problem with a brute force approach, which means that you're trying to span all possible future situations in order to make a decision about your current decision, you're facing what's called a computationally explosive problem. You need servers on your car to deal with this kind of what if, what else, everything. And that's not the approach. We offer something scalable to address this challenge. So I'll run through this. I warned you. This is just the structure of how we structure the concept of blame bottom up. In this case, it's top down, but we start from the definitions of corridor, what is a cut-in event, what is safe longitudinal distance, what is exposure time if we want to generalize to the case of occlusions, and we reach a definition of what is a situation of your blame. What is that case? We then use that, and this is not to be read, we then use that, we compose a very specific emergency maneuver, DEP. And we have a very strong proof that says that if you are applying a very, very temporally local, and this is something, if you apply a very, very temporary local check of your decision-making process, only checking something that takes into account very, very concurrent situation elements, you can guarantee the safety up to into the future. And that relies on our definition of blame and definition of that emergency policy. But this is, again, there is a very, very deep paper published on the topic. I really encourage you to look into that. And we're looking into the very good opportunities that we have to converse with the regulators, be that of private entities like Euro NCAP or governmental ones, to really instill this vocabulary and come up with a common discussion language for this safety of a vehicle, safety of decision-making vehicle. Moving onwards, this is an important statement that the right measure to judge how well a sensing system approximates reality, it's by the impact on the decision-making. You don't need to judge how well it measures the distance to the vehicle if that's not a critical measurement for the vehicle. And we then, as I said, disambiguate, and I don't go into these details, disambiguate what are these sensing errors that may cause safety-critical decision or misdecision, and what are these errors in the sensing that cause only drive comfort compromises. And we disambiguate them, again, based on that formal definition that we talked about. I'll move on to this one. As I mentioned earlier, the problem of decision-making is computationally explosive. You need to span all of the possible happenings forward and all of the possible responses of agents around you. And there are several approaches how to moderate that problem. All of these currently are not tractable or not successful approaches. The approach that we offer here for scalable method to deal with this challenge is to use the common semantic language. You're not talking in kinematics when you're planning your steps ahead. Consider a human driver or a human instructor. You wouldn't get an instruction that says, please drive 5 meters per second for 3 seconds, but it would tell you something semantically meaningful, like move 2 lanes to the left and position yourself behind that vehicle, or position yourself before that vehicle. And this is the kind of language we are adopting in order to make the computational planning problem much more tractable. Okay? We're planning by this well-conceptualized semantic language you don't need to do that on a milliseconds basis and on a meters per second basis. So let's look at the double lane merge. I think let's look at we're starting to see some videos. Let's look at the roundabouts as like one of the best inventions to deal with intersections, which are very weak points in terms of safety. And there we're running into a second problem of double lane merge, meaning 2 vehicles. This exemplifies this problem without the geometry of a roundabout. Vehicles that are interested to, the red ones are interested to go to the right, the white one are interested to go to the left, okay? And they have around 100 meters to negotiate that. And the driving policy solutions that we talked about, the semantic driving policy solutions that we talked about, along with the RSS, the responsibility sensitive safety model, yields the following results of round 0% accident. And the round 0 is very, very important here. It's not a mathematically sufficient proof of the formal safety model, but it is at least a supportive evidence of it. We show that by 100,000 runs, we had no accidents solving this negotiation problem. And more importantly, it won't tell you a lot, but it's running within 1 millisecond of computation. We were able both to solve the safety issue as well as scale the computational problem. This is the extension for occlusions. Here you see vehicles. By the way, all of these were trained, as I said, trained driving policy machines. What you see here is the vehicle making very intuitive decision of either driving slow close to the occluding vehicle or driving faster farther away from the occluding vehicle. Let's look at it again. Please watch the white vehicle's conduct. As they approach the red vehicles, they take some safety distance away so they can continue driving fast, so that they have enough time in terms of visibility time and blame that we talked about earlier to implement that. All right, here comes the quicker view of how do we solve scalable sensing solution. What do we offer as a scalable sensing solution? Human drivers rely on their eyes alone. All of the information is in the visual field of view. Neither of us have radars, LiDARs. It's a biological fact of that sort. We're not claiming that we are to solve an autonomous driving solution without redundancy and additional sensors, but one must recall that the visual field of view is a comprehensive perception space. In what sense is it comprehensive? It captures the full environment model elements. That would be the drivable area boundaries, that's the green carpet that you see, the driving path geometry, which is the geometry of road within that area, movable obstacles or road users, that would be the vehicles or pedestrians, and the rich family of semantics. Semantics could be explicit, like the content of a traffic sign or the color of a traffic light, and could be very implicit, like this pedestrian is crossing the road while watching his cell phone. That's another semantic cue that can be used while driving. Sorry, let's skip this one just in sake of time. In order to reach environment perception, redundancy enhancement and comfort enhancement, we need to deal with redundant sources of information for all of these elements of the environment model. That would be drivable area boundaries and driving path geometry, or let's look mostly on road geometry and road semantics, such as the traffic sign content, may only be served redundantly, or this information may only come from maps. There is no other sensor that can replace visual sensing of these cues. Lane marks, markings on the road, or content of traffic signs. There are other technologies like communication from the road or from the signs, but we are talking about a self-sufficient agent running in the current environment. Road users and some of the road boundaries which are structural, which are not just a gravel, for example, there is something there, may be sensed by radar and LiDAR sensors. We'll show just the approach of first about the mapping, talk about the mapping. What comes out of the need for the map to serve as the redundancy layer of road geometry is that the map has to faithfully represent reality at very low delay. Very faithfully represent reality at very low, meaning if outside of your house there is a new construction area, your autonomous vehicle will have to know about that construction area when you get there, okay? So our approach, of course, to the problem, and right now it's a kind of widespread approach to the problem, is crowdsourced mapping. Mobileye being a supplier for ADAS vehicles with cameras on board is using this asset, this fleet of vehicles, to harvest information which is useful for mapping the roads around us. This is a very scalable approach in the sense that we're using existing vehicles, existing technology, with no added costs to it, to allow this kind of harvesting of information. The harvesting of information, if we just look again into it, includes landmarks in the environment and the geometry of the road as we go within it. Second element of the map is, of course, aggregating this information into a valid and very, very accurate map. That it has to be accurate, and it has to serve any person who wants to localize itself within it, any agent. It has to serve landmarks or triangulation points content within it. So here we see a very complicated road network that we've mapped with our partners in Nissan, Ijima's team actually, working on mapping the Japanese highways before the end of next year by this approach. So last one is the third step is once you have that map, how do you use it in autonomous driving? In this case, what we show is that the map is the agent is localizing himself within the map based on these yellow landmarks that you see scattered around the image. And then we project the map to the image space. So what you see here, the green line, the orange line, the yellow line, is not real-time sensing of the road geometry, but rather projection of the map to the image to show that we don't really need the real-time sensing. That's the redundancy. That's exactly the redundancy that we prove by that. Okay, so last few slides, couple of slides. First of all is how do we integrate, in light of this view of safety, how do we integrate map, camera, and other sensors? First, we point out that since the camera contains all of the semantic information, all of the lanes and the driving paths, along with the objects, they are co-localized on the same sensing space. Camera serves as sort of the association space. This is where you're associating evidence from different sources, because the camera has the full coordinated picture. A single image has a full coordinated picture of all elements. Now you want to associate other sources of evidence, if it's a map or if it's radars and LiDARs, into that coordinated space. To make sure that you're aligned between the sensors and to make sure that you're time synchronized between the sensors. The map is a very good example to it. What you see here is a three-dimensional, sorry, you're not seeing it. What you see here is on the right side is a three-dimensional environmental model created only by cameras. What's the trick here is that cameras that were traveling this road beforehand created three-dimensional map. This map was used in the fusion process, projected onto the image, and then elevating the rest of the road users to 3 dimensions in a way that preserves the lane assignment, that preserves the very important semantics. We know which vehicle is within each lane because we coordinated it in the image space. Yes, no. Last outcome of that, and that's the last slide I have. Last outcome of that important, I'll just go to the green map that we had to summarize and see what is the last bit that I want to contribute here. So we talked about a formal model that uses the semantics of blame. What is, who's to blame, and what is my blame, what is the other agent's blame. We created this formal model, and based on that formal model, we derived requirements or a measure of whether a sensing error is a safety critical one or a comfort error. Then we moved to talk about how to approach scalably the decision-making problem, driving policy problem. And we presented a driving policy that implements the scalability with the safety. And last, we discussed the computer vision sensing, mapping, and sensor fusion. The last contribution is around sensor fusion. I just want to go to that slide and conclude that given that we offer a compliance check of any system, you can check whether it is RSS compliant with a very simple and implementable piece of code that we actually publish to the industry. We're getting a very good merit out of it, which is not trivial. It really separates out the perception used for driving comfort, the perception and the way you perceive the environment, the way you decide to describe the environment for comfort purposes, from the way you decide to describe the environment for safety purposes. And this decoupling is very critical technologically. It means that you can make completely different decisions when it comes to the shorter term safety critical elements of your decisions from the longer term comfortable driving metrics. And that's a completely different measures to the success of your technology. Thank you for your patience.
Yes, Dagan, thank you very much. Fascinating stuff, actually. Very interesting. We're coming to the last presentation that we had scheduled for this afternoon. Hopefully we'll have some time to deal with some questions if you have any. It's my pleasure to introduce again Anders Lie, now as a speaker, please. Anders Lie is a specialist in traffic safety working for the Swedish government for ages, I have to say. You're not that old, but definitely he has been a big supporter of Vision Zero with CLAS and really helping it advocate it around the world. He's also a very good colleague and board member in Euro NCAP from the start. I often call him the conscience of Euro NCAP, reminding us from time to time why we are there and what we are there for, that we don't get too much straight off to things that that are not really relevant. So without further ado, please have the floor.
Thank you very much. It's always nice to work together in this team. I have a great privilege today, and that is that I'm not an engineer. So I will not talk about autonomous driving or automated driving from an engineer's perspective. But I think it's important that we spend some time reflecting on where could this lead us. Because now we heard quite a bit about the legal aspects and the situational awareness aspects and technical aspects. And I will have a slightly different approach. And it could be meaningful to stay just to have the possibility to put questions to the other presenters after my presentation. The theme is future society, automated mobility, but the reason for this slide is really to cite Gordon Moore, who in 1965 said, "Change will never be this slow again." Sometimes we believe that we are in the middle of a very active period and it will be slightly more relaxed in a couple of years' time, but I think we should be aware that it will always develop faster and faster. So take this moment to relax, because change is slow right now compared to what we will see in a couple of years' time. I think it's good to remind ourselves that we are talking about the road transport system, a very open and complex system where we want people to actually live their lives, having the possibility for mobility, and that is an extremely positive thing. But it has downsides. The World Health Organization calculation of 1.25 million fatalities per year. As you heard Claes Tingvall say earlier today, we have killed around 100 million people in that system. So there's good reason to consider how can we change, how can we improve, how can we make things better. And I think the last 20 years, in parallel with Euro NCAP, it has been a growing acceptance for the zero target, the elimination of fatalities, the elimination of severe injuries. And it could easily be thought of as a trivial thing, saying zero instead of 100,000 or diminishing. But from the strategy point of view, it is very, very different to say it's something we shall eliminate compared to something we will try to do slightly better. You will have to backcast in different ways. You'll have to attack the problem with a different mindset. And as Claes said, taking the economical aspect away, which is slowly happening, is an eye-opener for many people working in the field of road traffic safety. But getting back to automation, I think it's important to look a bit at the bigger trends that we see in society today. And as everyone is aware, we are getting more and more digital. Just looking at the setup here on the scene, it is very different from when I started to give presentations on slides and very primitive tools. Digitalization is opening possibilities that we cannot really grasp because it's going so fast. We have the movement to shared economy. And as middle-aged males, perhaps we don't fully understand that we should share our car with our neighbor. But when we look at younger generations, it's quite evident that having a car being parked 95 to 98% of the time is a fairly stupid thing, how to use resources. Shared economy is changing our way of living, and I think it's coming quite rapidly. We see a growth in population in the world, and together with that, much of the expansion will happen in urban areas. It is not in the countryside that we will have a lot more people. We will have to build hundreds of very, very big cities in the next 50 years. Someone said, let's forget about the design of the cities of today and just focus on getting the new cities to be right, which is an interesting thought. We have an aging population, not only 1 year per year, but we actually live longer. We live at a higher quality of life, and especially with very high expectations of mobility also into very high ages. And we have, I would say, starting the last few years, a rapid electrification of the transport sector. The internal combustion engine is probably a bit of the past in the next 10 to 20 years. So we must think electricity in a way which we have not done in the past. And as an effect of all of those movements, the livable city is becoming more and more important. If you see mature cities around the globe, they all try to talk about the positive things they can deliver to people. They want to be greener, they want to be more comfortable, they want them to be more attractive to people. So livable cities is a very, very big movement. Errors. We can always debate whether it should be 90 or 95 or even 100%. There's always an element of human error when things are going wrong out in the transport system. And I think a safe system or a Vision Zero system is very much about absorbing the errors and mistakes that people do. And probably it's also about absorbing the errors that automated cars can do. Because if we build that margin into the system, that can be used by humans, but it can also be used by the automated cars. And I would say this is, since 20 years, the paradigm for road traffic safety. Absorbing errors and mistakes, not trying to build the perfect human being. Model vehicle safety has developed tremendously, and 20 years of Euro NCAP is a nice example. If we look at the cars that hit the market 20 years ago, that was the first generation of airbag cars. And with the airbags came the demand for a more stable structure. That is now everyday practice. And when I make calculations in Sweden about the improvements in road safety, about 2/3 of the annual improvement could be attributed to the exchange of vehicles. We exchange 5–6% of the vehicles every year. But anyhow, 2/3 of the improvements we see come from better vehicles. And we have seen automated functions that are virtually eliminating some crash types. ESC is virtually taking all loss of control out of the system, also in Sweden with snow and ice and everything, virtually eliminated. We see how AEB is actually taking vast majority of low-speed rear-end crashes away. We see how lane departure warning has already shown a 50% reduction in the warning mode, enhancing that with support could give even more. And we have other technical systems in the cars like seatbelt reminders, the good support for not speeding, driver alertness, etc. And together with these developments, we see how cars have developed a primitive sense of awareness for the situation. And we heard a very nice presentation about how Mobileye is looking at situational awareness. What are the sensors? What are the approaches to that? So it doesn't come as a surprise that many people are looking at automating, putting all those functions together and automating the system. But from the safety perspective, we must also understand that with the developments, with the knowledge we have, we will not have a lot of in-car fatalities in the future. I would say if I would manufacture cars or in any way control and guide vehicle industry, I would say look a lot more of the people around the vehicle, perhaps more than the people inside the vehicle. Don't forget about them, but that's very much to do outside. So what do I believe is characteristics of an automated car? Well, first of all, I think safety will be a given, and it will be the limiting factor. Because it's something very strange happening when I go from being a driver to being the passenger. And we see that in the willingness to pay for safe aviation. We see it in the willingness to pay for safe trains, which is a lot higher compared to the willingness to pay as a driver. So expect a lot higher safety demands when you cannot blame the driver anymore. It will be a new situation. So it will be also a situation where perceived safety is a lot more important than before. Because if, as Ola has been talking about, trust isn't there, you will not use the function. So you must perceive the car as being safe. And I think also that the full crash avoidance will be a lot more important in the automated car compared to the manually driven car. But over and beyond everything, avoiding severe injuries and fatalities will be there. And it will be a very tricky discussion about how much of crashes, how much of reduced comfort am I prepared to offer. So these cars will be careful, they will be polite, they will be law-abiding, which is extremely good for road traffic safety, and they have to be social. They have to talk to the people around them. Situational awareness for them should also support situational awareness for other car users, pedestrians, bicyclists, so we understand the intention of each other's. And I just want to draw your attention to the Vienna Convention. People often cite the Vienna Convention, but a different paragraph than this one, but I'll read it out. Road users shall avoid any behavior likely to endanger or obstruct traffic, to endanger persons, or to cause damage to public or private property. That is, of course, also extremely valid when there is a computer driving. exactly the same care will be needed. And we know that if we are uncertain, low speeds or separation is a way forward. A car driving in 5 kilometers an hour can probably stop in 15 centimeters. The situational awareness can be very limited, still safe. Or you will have, as illustrated here, you will have to have very good sensors, knowing things far away, because in the end of the day, you should be able to stop for anything obstructing or endangering your journey. So for me, with the coordinates saying the car must be safe, it must have a perception, and it must be able to stop, the challenge will be efficiency and not safety. So probably we will see the first automated methods being at very low speed or in fairly trivial traffic situations where you can fulfill this. But trying to move this a bit further onto mobility, there are some, I would say, almost philosophical questions. Should we make the system as of today automated? Or should we look at a completely different road transport system? Very much of what we heard so far today is about more or less substituting the driver of today with a computer, not elaborating so much on what could be the new possibilities. And again, my personal view is substituting a middle-aged male in his car on his way to the job with a computer so he can be in the car reading the newspaper. That is not a big thing for mankind. Could be on the individual level interesting. And having cars parked 96, 95, 98% of the time is not a very clever thing. So this is just an example how one megacity has decided on their mobility plan. And the interesting thing is on the far right. It is Mexico City. It is 23 million daily trips. It's about to Sweden in size, around 10 million people. But they have decided to put walking on top of the pyramid. That is priority number 1. People should be able to walk in their city. Priority 2 is people should be able to bike in their city. 3, public transport. 4, logistics, getting goods in and out. And on their priority scale, private cars, private motorcycles are in the basement. Imagine this being the design paradigm for our cities in the 40s, in the 50s, when we designed everything for cars, when we actually pushed our kids out of the streets to give us middle-aged males priority in the traffic. This is extremely radical, and it is coming from a very important town. And I would say they are not unique. I think this is very much the future in many of the megacities. So for me, at least, mobility will be the future. It's not driving your own car. I think these low-speed pod cars, which is not the future, it's already here. It's running on commercial basis in some of the cities. That will be a big thing. How to get goods out to people, either in those micro Starship things or in the Google patent where you more or less have a container you put out automatically where you can collect your goods. How automated modes, walking and biking, is getting a good marriage with public transport will also be extremely important. The multimodality, not being in my box all the way, but accepting that I can be in different boxes. But we must also understand not everything is the same. The needs in the rural areas, the needs in the bigger cities, they are very, very different. So I don't think we will flip a switch and go from being manual to automated overnight. So that's an important thing to understand. So for me, the digitalization is the fundamental factor to start to get mobility as a service. Telling the computer world, where am I, where do I want to go in the most efficient way. The shared economy, we will see car sharing on completely different new ways. And where a shared car, of course, can go home to my parking lot or to my door, standing there when I need it. It's not used by me all the time, so it's hovering around, getting to me. And also how the car sharing is marrying with public transport. So for me, loving cars, public transport is a very interesting sector in the future. How could you make that automated, attractive, and efficient for everyone? I think for aging population, also the automated functions could become extremely important. How can all the sensors, all the situational awareness, all the actuators support me in the future, my mother today, not to reverse into things, not to lose situational awareness, having the emergency braking, everything like that. Because we will demand high-quality mobility also when we are getting older. I think the electrification is going extremely well hand in hand with automated cars. I can have a car which has the right amount of energy for my journey. I can have a car which is going away, refueling the electricity and getting back to me. So the small cars, the pods, and the logistics will be electrified in the near future. And definitely, I think from this we will have a more livable life in our cities, but also in our countryside. So thank you for my moment on the scene.
Well, thank you, Anders. When I started opening up this session this afternoon, I think we talked about automated driving being such a big topic. And even if you restrict it to the safety dimension, I think it still would allow us to talk a few days more about the topic. So what we have to really try to do this afternoon is to create a kind of a matrix for you, looking both at the societal side of things, which Anders just did, to the individual interpretation of what automated driving means for the consumer. The technology on one side, regulations on the other side. So it all has to come together one day or another. And that's the space where we are in at the moment. So I hope that you enjoyed this kind of multi-faceted approach to the topic at this moment. We have some time still for questions. We're supposed to finish at 4. It's 3:45 now. I think only Brian has left, I think, but all the other panelists are still here. So I think they are certainly willing to answer any questions that you may have. On the other hand, I can promise that most of the slides can be shared with you, as long as I have permission to share them, of course. And we will do that. We'll contact you via email with a link so you can download and see them again. Are there any urgent questions to the people that have presented the material? I know there's a lot to digest.
I'm Søren from Denmark.
Yeah.
I have a general question. Does it in the future make sense to do a crash test of a car which can't actually crash? How will Euro NCAP deal with this for the future, that the car will not be able to crash? Does it make any sense to do crash test for the future?
Ola, you want to give it a try? As a restrained developer.
Yeah, but obviously, I mean, we're going to have a mixed traffic for so many years. So yes, there will be cars that cannot crash, but they will be crashed into. So yes, there's a need to rate and to design a car from being crashed into, which is a load case maybe you didn't think of. Or was that answering the question?
Yes, but could you change the way to test the car?
Okay, yeah, that's...
Well, I think certainly in our roadmap that we just published today, there you will see a section where we discuss this in particular. So we come from an area of passenger safety. We have, from 2009, really stimulated avoidant type of systems to come into the rating. I think what we see now is the next phase would be merging these two together. And that kind of opens up the question that you just posed, is how are you going to assess systems, passive safety systems that actually are deployed or not deployed based on the circumstances, based on what sensors see around the vehicle. And that will probably have to be dealt with, and that's what we want to do, want to deal with going forward, where we actually allow the manufacturer to actually use sensor information in the crash test to optimize. From a worst case perspective, however, we always have to assume that there may be situations where the sensors are not perfect, and that may bad weather conditions or other sorts of problems with sensors that actually would mean that the car doesn't have any information and needs to rely on deployment of its passive safety systems. So for us, these are two fundamental things that we want to keep in the rating system. The worst case scenario, the protective of the consumer at the end of the day when nothing is there anymore, and how do we encourage the further integration of passive and active safety systems in more efficient safety solutions for consumers.
I think the photo from Japan with a car flying over the median divider is an example of situations where the passive safety will have a very important role also in the future. But of course we need, in the longer term, to learn from the efficiency and the reliability of the active safety systems. And when we see that they are reliable all over, of course we can have a renewed discussion about what could happen with the road design, what can happen with the vehicle design.
Anybody else has a question? Yes, sorry, can't see you.
Thank you. Michael Payne from Australia.
Michael.
I'm very interested in the Mobileye development of basically knowing what the characteristics of the road ahead, because one of my concerns about, say, steering crash avoidance is what are you steering into? And it seems to me you're knowing more about the characteristics up ahead than just what the cameras see.
Eris, do you have a answer? It's your long-distance awareness. How much more than the camera can see will you use in your algorithms, in your decision-making? If you come up here, you get the microphone on. And
Thank you. Okay, so thanks for the question. Thanks for the question. I think that part of the disambiguation of the importance of sensing for safety aspects versus the importance, not the importance, but what implications the sensing system may have on safety critical aspects versus what implications the sensing system may have on driving comfort. And I think this disambiguation answers or addresses your question. In most cases, the very far range is linked to drive comfort and drive longer term planning. Whereas when you come to deal with safety critical decisions by that safety model that we presented, you're usually looking, even in highway speeds, at much shorter distances. So you have in these areas also comfortably, without over-specifying very fancy other sensors, looking at, with camera, the cameras have the advantages of scaling gracefully with resolution. You can reach far distances if you have the right optics. They have other limitations, visibility conditions. They don't have depth perception directly. But this disambiguation relaxes the specification of far-range sensing needs, right, formally.
Thanks. Cheers. One more question? Yes.
Hello, I'm Ingrid Skogsmo. I'm at this time working at the European Commission on the research side. We talk a lot today about automated vehicles here. Sometimes in the debate you hear about connected, cooperative, automated vehicles. So I was just wondering, do you have any thoughts on how connectivity or cooperative driving could enhance getting forwards to Vision Zero or in Euro NCAP's future?
Sure. So if you would have a look at our roadmap, there is a section on V2X technology and how we see it becoming important. From our discussions with many OEMs that we had in the preparation of our strategic roadmap, we found out that I think this is on everybody's radar. However, there are still some big hurdles to make as far as standardization in the marketplace before we can really expect this to be adding value in the safety equation. So yes, we believe that this, of course, will be the next revolution where we can actually extend our visibility, as we have seen from Mobileye's presentation, much further than what the current sensors can do. Specifically for the more vulnerable road users, like powered two-wheelers, this will be an ultimate solution, I think. The time frame that we have currently put it is more like 2024, just because of what we believe still needs to be agreed on in Europe and between the European member states in terms of standardization of communication between vehicles. Anders, you want to say a few things more?
Just adding perhaps that communication is already today essential for many strategic decisions in the driving and perhaps coming into the tactical ones. But when you get to operations, when you go to things which is here very close, I don't think it will happen in the next 2 years that communication is the key. But as Michiel is saying, as technology is developing, standards are developing, and the market is slowly penetrated by those systems, the capabilities and the possibilities will increase significantly.
Thanks for your question.
Jacques Wismans, SafeTech and Chalmers University. I hope you can see me.
Yep.
We heard today the figures of 1.3, 1.4 million fatalities per year. 80% of these fatalities are in developing countries, and of these 80%, 60 to 80% are vulnerable road users, so the cyclists, pedestrians, and a lot of motorcyclists as well. And with trends like e-bikes, higher speeds for bicycles, and so on. So my question to the panel is how you think that automation can help reducing these type of fatalities. Since particularly also many of these are not impacts with cars.
Ola, I remember you had an Indian data source. I guess you did that for a reason?
Yeah. Okay. Partly answering the question. So the calculations I showed was basically major impacts actually on this type of accidents, because a larger part is caused by vehicles colliding with two-wheelers and pedestrians. So indeed we do see this dramatic decrease of fatalities of putting this technology into the cars. But you are addressing maybe that people will change their behavior during these years and going by e-bikes, for example. And then the question is maybe how can we use the same technologies in two-wheelers? And I'm not the person to answer that, but I guess at least it's a good start to have a battery in the vehicle, yeah. in the two-wheeler.
I think we must remember that to some degree the cars, the buses, the trucks can address the powered two-wheelers. But on the other hand, it's getting more and more absurd that we allow unprotected road users at speeds up to 70, 80 kilometers an hour when we have safety in focus. And that is why I'm a keen e-biker, because the e-bike has a speed which is more relevant for our biomechanical levels. 30 kilometers an hour on its own is not that dangerous. And then the real risks are coming together with the interaction with other road users. And the second thing is really the economy of scale is, of course, making it possible in the future to transfer a lot of the knowledge, a lot of the technologies, which are way too expensive today to put on an e-bike or on a simple motorcycle. It is doable to put them also on those modes of transport in the future.
All right. Okay, then I think it's time to wrap up this afternoon and also the day for Euro NCAP. Thanks everyone for coming. It's really appreciated from our side that you're here and willing to celebrate with us. I want to thank, obviously, the speakers for coming and refer you to tomorrow when the Jacobi conference starts at Elsenveld, which is about 15 minutes from here walking. So we look forward to 3 more days of intense research discussions, specifically on biomechanics and what automated vehicles will do in the future and change circumstances inside the vehicle, but also, of course, on vulnerable road users and other means of transport. So thank you very much.
Thank you,
also,
Michiel. Thank you,
Anders, for helping me, and well, have a good evening and a good way back. Thank you.
Good evening.